All right. Fantastic. All right. Okay, so once again, everybody, my name is James Skelton. I am a technical evangelist for Paperspace, and welcome to today's Tech Talk. We're going to be talking about restoring and upscaling damaged photos with GFP-GAN and also real ESR-GAN. Before we get into the actual material, I would like everybody here to log into Gradient and navigate to your private workspace and either create a new project or go into a project you feel comfortable adding to. If you don't already have a Gradient account, go ahead and sign up. It's easy and free. We're going to be working with the free GPUs today, so you only need a free account to participate. The other important thing I want to mention is if at the end of this session, we're going to actually be uploading pictures to be restored and upscaled using a Flask app that we've deployed with Gradient deployments. So if you don't have a photo that you want to have upscaled, go ahead and go to reddit.com/r/estoration, which is still my favorite Reddit subreddit name I've ever heard. It's just so great. And grab any photo there that you think has a good picture of people that you feel like would serve as a good example for your own purposes. All right. Let's go through a quick table of contents of the, oh, sorry, Shane. I've just posted the link to the slides again in the chat if you don't have them. So go ahead and open that up. And you can save a copy in your drive if you want to mess with it or do anything. Can I get a B that everybody has access to the slides? I just want to make sure. All right, seeing some Bs. All right, cool, wonderful. Then let's get started. So the first thing we're going to talk about is just an intro to AI photo restoration. This is kind of jargon, really, talking about the capabilities and the challenges involved in a photo restoration task. Then we're going to look at some past approaches and methodologies. These are specifically convolutional neural nets, autoencoders, and transformers for photo restoration. It'll be a brief summary. Then we're going to look at real ESR-GAN, which is I guess you could call it a sibling to GFP-GAN. They actually work in tandem, and I'll go through how that works. But real ESR-GAN upscales photos, but their backgrounds rather than the actual subjects. So we'll talk about how that works and what's going on under the hood to make it work. Then we'll look at GFP-GAN itself and how it works under the hood. I've got a nice example of what that final result will look like here for you on the page. As you can see, I got this blurry picture I took from r/estoration. And when running it with GFP-GAN, we get some really nice faces here. So much clearer. Finally, we will actually look at using GFP-GAN within Gradient. This is specifically using Gradient notebooks first, and then looking at a deployment that I created with a Flask app. Real straightforward. Looks like I double typed that. Excuse me, all. Cool. So without further ado, let's jump into it. So, excuse me really quick, sorry. Just making sure I'm pulling up everything correctly. All right, so let's introduce some relevant jargon for AI image restoration. First up is denoising. So if any of you, and I assume many of you, are familiar with working with statistics, noise refers to unexplained statistical variability in some data sample. So in the context of our image and image restoration, this would refer to random variations in brightness and color in the image. And denoising itself is the practice of removing these effects from the image. And I just took from Google this sample here. It's a noisy picture of a deer. If you look closely, you can see there's this kind of almost white pattern emerging in the background, and it's also sort of present on the fur. And then the denoising algorithm here basically smooths over everything. So as you can see, denoising by itself doesn't do that much to actually restore the quality of the picture, but we get a substantially better idea of what the original might have looked like without the effect of the noise in the way. Up next is deblurring. This one is a bit more straightforward. The process of removing blur from images. Deblurring recovers a sharp image, we call that S, from a blurred image B, where S is convolved with the blur kernel to generate B. And here we've got an example of just a blurry photo of what looks like an outdoor mall, also taken from Google, and a cleared up version of the same photo. You can see there's a lot more resolution and definition, and removing blur has a substantial effect. Okay. Now let's move to the next slide. Up next, we have demosaicing. If you were to Google this, you'll see that it's spelled a bunch of different ways, sometimes with a K, go figure. I just thought that would be worth mentioning. But demosaicing itself is the process of reconstructing a full resolution color image from data acquired by a digital camera overlaid with a color filter array. And above, I've got a really nice diagram that I've got the link to the paper referencing it here, showing how we have these mosaic frames. The frames are then pulled into an RGB versions. Then they are fused into a restored single full frame. Finally, the last thing to bring up is super resolution. Resolution imaging is a class of techniques that enhances the resolution of an imaging system. Pretty straightforward, sounds like the name. Here we have an example of a blurry photo of, I'm guessing that's a construction worker, that is then radically up, well, the resolution is upscaled, I guess you would say. Oh, excuse me. Significantly better quality. So if we look at all of these holistically, we can see that denoising takes away this effect of, you know, just essentially like improper conversion. You know, you'll get noise like this from taking something and compressing it like JPEG compression does. Deblurring removes the potential effects that could actually be caused by the person taking the picture, most likely. Demosaicing allows you to get a full understanding of the color inputted to the image, and super resolution actually upscales the resolution. So when you put them all together, you get a very effective picture of how image restoration can be done. So now that we've introduced some of the relevant jargon, let's talk about some past approaches and methodologies that came before real ESR-GAN and GFP-GAN. I'll talk about this more in a moment, but GFP-GAN and real ESR-GAN are both about 6 months old. So very, very new, not quite bleeding, but cutting edge technologies that we're going to be working with. Convolutional neural nets kind of were the start. Because CNNs have really large and computationally expensive receptive fields, there was in order to actually use CNNs to make this work, they basically need to be optimized so that the deconvolutional layers could upsample the feature maps and recover the image details in an efficient way. CNNs are then capable of reconstructing the images with reduction in noise and image artifacts specifically, or most effectively, I should say. And they can basically go from fine to coarse mapping of the image features to do the generation. Up next, we have convolutional autoencoders. They learn how to decompose data, image data into latent and spatial features, and then using those representations, they are able to reconstruct the image. So it has an encoder and decoder layer. The convolutional layers capture the abstraction of the image contents while eliminating the relevant corruptions. This would be something like noise, blur, JPEG artifacts, etc. Then the deconvolutional layers upsample the feature maps and recover the details to get the generation of a higher quality version of the original image. And finally, transformers. These are a little bit more niche and less common, but the paper I found about transformers used a self-attention mechanism to capture global interactions across the different contexts and in a variety of different visual difficulties. the transformers divided, the ones that I looked at, divided the input itself into patches and kind of batched through them and analyzed each patch separately before reproducing the image in a step per generation. And we're able to get like an upscaled and restored version of the photo made piecewise. So these are three different approaches. They are all, there's a pretty wide variety. I think there were, three or four examples I found for transformers, something like 20 for autoencoders, and because convolutional neural nets have been used for this for a long time, something like 50. They vary a lot and their success varies a lot. In general, though, you're going to find that a GAN will outperform these, especially these modern GANs that we're going to be looking at today. And so without further ado, let's actually jump in to the subjects of the day. So real ESR GAN was introduced originally in 2021, and it is capable, well, after being trained with synthetic data, of enhancing general image backgrounds and non-facial foreground details in common real-world images while removing annoying or unnecessary artifacts. And I've got a diagram here kind of showing how that works, which in practice really is, it's an evolutionary step on from the original ESR GAN, where it takes what's called a high order degradation process to model practical degradations in the image and use sync filters to model common ringing and overshoot artifacts. Really quick, a sync filter is an idealized filter that removes all frequency components above a given cutoff frequency without affecting lower frequencies and has linear phase response. Ringing artifacts are artifacts that appear as spurious signals near sharp transitions in a signal. So think like if we were using a photo of a circle and it gets jagged at the edges where the pixels are not able to actually portray the circle curve. And finally, overshoot is the occurrence of a signal or function exceeding its target. Cool. Real ESR GAN employs several essential modifications to increase its own discriminator capability as well and stabilize the training dynamics. So it is able to actually restore most real-world images and achieve better visual performance than a lot of previous works. And it's really practical to use in real-world applications because it runs very quickly. So now we talked about what it is. Let's talk about how it works under the hood. So, excuse me, sorry. Got it. Sorry about that. I had a confusing thing. Real ESR GAN uses what's called higher order degradation, as I mentioned before. To explain what that is, the degradations are modeled with several repeated degradation processes. So looking back on the image here, we get this stage here where it's using the random processes to make changes to the initial input. And then this iterates to second order where more random changes and effects are made to help kind of introduce some of the effects of blur, downsampling, noise, JPEG compression, etc., to the image so that it can learn how to deal with these traits. Sorry, to go on, empirically, the second order degradation process offers a good balance between simplicity and effectiveness. And high order degradation modeling itself attempts to mimic the real degradation generation process that we see in real life. So as I mentioned before with the circle, sometimes you will have a photo uploaded and it'll get downloaded, re-uploaded, downloaded again. And eventually you've messed with the original file so much that it's actually got artifacts and changes that go through with it. So basically what the real ESR GAN is doing is mimicking that so that it can learn how to deal with those sorts of traits in an image. Because of all of this, the degradation space is much larger than its predecessor, ESR GAN, and training becomes pretty difficult. or it would be difficult if they hadn't made this modification. Specifically, the discriminator requires a more powerful capability to discriminate the realness from the complex training outputs, because there's a much finer difference between the real image damage, so to speak, and the induced image damage that we are creating in the ESR-GAN training process. So in order to do that, the authors created and used a modified VGG discriminator that is in a UNet architecture. So in practice, the real ESR-GAN is able to learn various low quality versions of the input image with random effects of the blur, noise, etc. applied, and each operation is selected randomly. Oh, sorry, typo. So distracting. And then it is able to fully connect from course define what these effects are doing and allow you to regenerate the image. The next important part I want to mention is that UNet discriminator. And I've got a nice picture here showing how, if you look on the left side, we've got this picture of just two white squares by the looks of it with a foresty background and sky. And you can see that there is a distinct demarcation where the white is, showing that the signal is caught up. This is what we call a spectral norm. The UNet structure and complicated degradations, as I said, increase the training instability a lot. So in order to compensate for that, they use spectral normalization regularization to stabilize the training dynamics. And moreover, they were also able to observe that actually using spectral normalization is beneficial because it alleviates some of the over sharp and annoying artifacts that are introduced during GAN training. With those adjustments, they're easily able to train the ESR-GAN and achieve a really good balance of local detail enhancement and artifact suppression. Cool. So that's real ESR-GAN. Now, really quick, I'm going to have a brief break. I would like all of you to follow along with me because we're going to set up our notebook for the next part of this. I've got a few more slides to go through, but as they're long, I figure we could set up our notebook while we do that. So if everybody could go to consult.paperspace.com, so the gradient consult, and then navigate to a project and team of your choice. And then can I get B's in the chat once everybody's done that? And then I'll show you how to actually set up the notebook. Give everybody a second. Yeah, no rush, no rush. Yeah, you can totally use a private workspace if you don't have another team. If you just created an account, you might only have a private workspace. Perfectly fine to work in there. I just want to make sure everybody was working in the section that they wanted to work in. I'll just give everybody another minute to make sure everything's set up, and then we'll do the walkthrough. By the way, this session is being recorded, so if you're unable to make an account right now for whatever reason, you'll be able to follow along later, or you can just use the notebook slides to do so. So, nay bothered. Don't create a notebook yet, Ayush. I'm going to show how to do all of that in just a moment. I suggested you create a project just because I figured some people wouldn't want to work outside of their private, wouldn't have a, excuse me, what's the word I'm looking for here? I got distracted by the comment. It doesn't have a team yet. Okay, that's what I meant to say. Workspace URL. I will paste that in the chat. All right, so now that everybody's had a chance to either create an account or log in, go to the notebooks tab in whatever project and team of your choice. So that should be, if you just click that to get into Gradient, it'll take you to this projects page in whatever workspace you're in, and then you can go into that project. Then go into the right corner and click Create. Once you've hit Create, you'll be taken to the Create a Notebook page. In this first section, we have our available runtimes. These are essentially Docker containerized bits of installations that can help facilitate whatever your task is. In this case today, we're going to be using PyTorch, and we need a GPU-enabled machine. So scroll down to select a machine. And I recommend all of you use a free machine. If you run into an availability problem, throw it in the chat, because I know there are 30 of us here, and that may just because free GPUs are always in high demand, that may cause an issue. But for now, click free GPU. You can set auto shutdown to however long you plan on working on this after the session. I recommend an hour though, because we should be done with the notebook within the time that we're still talking. And then finally, go down to advanced options. And if it's not toggled, toggle this so it's going to the right so that you have this workspace and container information available here on the right. Get rid of the workspace URL for PyTorch and replace it with github.com/gradient-ai/GFP-GAN. And once you've done all of that, so you've got PyTorch runtime, a free GPU, and you've pasted this into your workspace URL, click Start Notebook. Yeah, see, I already have one running, so it's okay. And it should begin running. Sorry, I had a question in the chat asking me about what this step does. I'm assuming you're talking about the workspace URL. The workspace URL, it's essentially, it's a GitHub repo, and what it does is it basically clones that GitHub repo into your new instance and sets that up as your workspace environment. So it'll be the folder that you're acting in. In this case, you need to do that so that you can get the inference GFP-GAN and run GFP-GAN to IPyNB files. It should take about 2 or 3 minutes to set up. So let's go back to the slides. And before I go back into it, can I get a B in the chat that everybody was able to successfully make a notebook? A container image is required. Did you click a runtime for PyTorch? Yeah, so make sure that you first click the PyTorch runtime, then select your GPU. I suggest a free machine. You shouldn't need anything more powerful for today. Okay, out of capacity. All right, everybody. We apparently run into an out of capacity problem. I'm really sorry about that. There should be a possibility that you can, let's see, there may be P4000s as well. I don't actually have my free account set up in here. All right, for now, just follow along with me in the notebook and try again later. I'm sorry about this, y'all. I'll send out the information for setting this up. I suspect that most of you have an instance working, but there may be a few of you that get an out of capacity. Just try again in a few hours. Unfortunately, this is lunch hour in a lot of the US, and a lot of people might be using the images for various projects in their time off. In the meantime, I will, oh, beautiful. All right, cool. All right, so everybody's working. Great. Great, great, great. That's the best news. Okay, then let's go back into GFP-GAN. So GFP-GAN is the subject of the day. We had a lot of build up to get here to understand how it works. it was introduced just last year, and it stands, GFP itself stands for Generative Facial Prior. And for those of you who don't know GAN, that stands for Generative Adversarial Network. And it restores with a previously unseen degree of realness and fidelity with fewer artifacts than its predecessors. It even does color. It's a really, really, really nice facial restoration algorithm. And we've got this example down here provided by the original paper writers, comparing and contrasting some different image restoration neural nets and algorithms against their own. So on the far left, we have the input. So you can see it's a, oh, you know what? Sorry, I actually have a bigger version of this. Let me pull that up. And I can't escape this page. All right, there we go. All right, there we go. So as we can see, there is some significant blur going on in all of these input photos, probably the least in the first. And each of the different models that we're comparing here does a different kind of decent job at replacing the missing details. So high face GAN seems to do relatively well with the little girl, but there's some, obvious artifacting going on here. And then, in this pulse example, for example, it seems like a man's face has been pasted on. So previous iterations of image restoration, especially for faces, have not worked in an ideal way, which is why the success that we can see here is pretty astounding. I mean, this is stunning improvement in quality. All right, so to summarize and really how it works in practice though, oh, sorry. Got a good question in the chat I want to answer really quick. Why is it only created for face and why not for full images? My understanding is that it was optimized for faces using StyleGAN 2 as the generative facial prior. So because the StyleGAN 2 model that we're using was trained on faces, it only works for generating face photos. And I'll talk about how it works in conjunction with StyleGAN 2 in just a moment, but to be succinct, that's why. So that's why it's really nice when paired with real ESR GAN, because together you can upscale a person's face and their entire background. So it's a really robust pairing. Yeah, and actually that dives really into what I was about to say. They leverage really rich and diverse generative facial priors for their blind face restoration. Those priors contain sufficient facial texture and color information, allowing them to jointly perform face restoration and color enhancement. Thus, the authors propose the GFP-GAN framework with delicate designs of architecture and losses to incorporate a generative facial prior. GFP-GAN itself, with the, oh goodness, I'm sorry. Something has gotten into my thing. Oh, okay. What I was about to say is that it achieves a good balance of fidelity and texture faithfulness in a single forward pass, and extensive experiments have shown that the method achieves superior performance to prior work on both synthetic and real-world data sets. But the real usefulness of this is in real-world applications when paired with real ESR GAN. Pardon me about that pause there. Okay. So let's look under the hood a little bit. So this is going to be pretty involved, but this quite literally is the most succinct way of explaining how it works. So please bear with me. First, the degradation removal module removes blur, low resolution, noise, and JPEG artifacts while extracting the clean features of the image as f-latent and f-spatial. The latent features are then transformed into an intermediate representation W and input to the generative facial prior. So as I said before, that generative facial prior is a StyleGAN 2 model that was trained on faces. So what it's doing is it's capturing the representations in our input image and trying to map it to how StyleGAN produces faces. So we're using StyleGAN to do a lot of the work, which is beautiful, really smart. The GFP then maps the input image to its closest latent codes, Z, and generates the corresponding output with a pre-trained GAN. The spatial features are fed into corresponding channel split feature transformation modules, which are used to scale and shift the output at each stage of the generative process. And altogether, the GFP-GAN learns how to reconstruct the same image at different scales and resolutions in order to fully comprehend the input's features from fine to coarse while outright ignoring artifacts, blur, and noise to generate a really nice upscaled and restored version of the original image. So I know that was a lot of talking without a picture. So here is a diagram explaining exactly how that works. First, we have this UNet degradation removal module. It maps the latent codes W to be input to the generative facial prior. It takes the spatial information out to the channel split SFT, which uses that to modulate the outputs of the GFP. It does this iteratively from fine to coarse to improve the quality of the image. So we can look over here. I know it's a little small, I'm sorry, that the original input is fairly blurry and that this final output is fairly high quality. In order to accurately do that, the predicted features are, when they are synthesized, they use L1 and perceptual reconstruction loss, adversarial loss, ID loss, and face component loss, which are all obtained from small local discriminators in the face. Specifically, like the eyes and mouth are the worst offenders. In my example before image, you might have, oh, I guess I closed it, excuse me. In this example, you might notice that a lot of eyes are where you're gonna get, it's hard to see, but there's distinct noise in this woman's eyes forming here. It's an artifact here in the glasses. These are just places that StyleGAN, it can't work as well on for a plethora of reasons. But adversarial loss, facial component loss, and identity preserving loss help to mitigate a lot of that. All right. So now that we've gone over how they work, we can see that real ESR-GAN restores and upscales general images, backgrounds, and foregrounds without faces. And GFP-GAN restores and upscales faces specifically. So together, we have a fully realized framework for handling both cases, and we can use them together to create a more successful and generalizable photo restoration process, which is exactly what the team behind GFP-GAN has done. Oh, okay. So let's all go back to our notebook. And can I get B's in the chat that everybody's notebook has started successfully? Cool, cool. Okay. All right, so now that everybody is in here, the first thing I would like all of you to do is go, if you're not already seeing this file manager, click on this, file tab on the left, and then navigate down to inference_gfpgan.py and open that file up. So this is where the actual run is done in this main function. Oh, I got another excellent question. Will it also remove any filters on the image, like an Instagram or Snapchat filters? My understanding of how AR works is that it overlays the thing on top of it. So there wouldn't be anything remaining of the original. At least I think that's how Spark AR works. So that's specifically the Instagram and Facebook filters. I'm not sure about Snapchat, but my suspicion is no, that it would not be able to do that. Like if you were to take a selfie with the dog face that was really popular a while back, I'm sure it still is. I bet you that would really confuse this model. Although admittedly, I haven't tried. Just because it's only trained on normal faces like real life data, it has no reason to be able to handle, frankly, an outlier. But excellent question. Thank you for asking. And I do see the other questions in the Q&A. I haven't answered them, Ariel and Ala, but if you'd like me to, I can just throw it in the chat. I just figured you were fine with me waiting if they were in the Q&A. All right, so let's look at our script here. So the first thing to notice is we've got a parser, argument parser, series of arguments being added. The ones that I think you should, yeah, there is one, 34 and 36. Good catch. I wonder if, I don't know if I did that or if that was the author. Oh, got a good suggestion in the chat as well. In the top right, if you want to change into dark mode or light mode, you could just toggle this. I know some people really prefer one or the other. The reason I'm wearing these glasses is because I don't like bright lights. So dark mode it is for me. All right, let's look at some of these arguments. The first one that I think is really important is upscale. This is just an integer, and it basically tells how many times bigger the final image will be. The next one that is important is model path. This is going to be the path to where you have your model. This isn't going to be a concern for us today because we're just going to dump it into the specific place they have it in the repo, or they suggest you have it in the repo. Next one is BG upsampler, background upsampler. This is where real ESR-GAN comes into play. So you need to have this in here if you want to have your background restored and upsampled. And the last one I'd argue that is, oh, sorry, nope, two more. Test path, this is where you have your inputs. So if you wanted to directly input some image you have, like you got from r/restoration, or a photo of your grandma from 50 years ago that got water damage, I don't know, there's a myriad of situations, then you can upload it directly, and I'll walk through how to do that in just a moment. And this test path argument takes the GFP-GAN to the right path for the inputs. And finally is aligned. I'd argue this one is really important if you want to get optimal results. Aligned will Align takes the images and actually takes the faces and puts them in the center, and then rotates them so that they are, their face is aligned with the orientation of the photo. In a nutshell, computer vision does not play well with rotations, shifts, turns, things like that. Having everything be straight works better, which is why you're able to get optimal results with the aligned images. Cool. So it takes in those arguments and make directories as needed. Next thing to point out is where the background upsampler is instantiated as needed. So if you did say you wanted real ESR-GAN and you have access to CUDA, then it will import real ESR-GAN from the repo that we installed, or the library we installed, which you do at the very beginning in the notebook. I'll point that out. It uses that to get the model path and instantiates it as our BG upsampler. And if you say you don't have one, if you say none, then it'll just won't do it. Then our script instantiates the GFP-GAN itself using our arguments. Excuse me. And finally, we take our image list from the test path argument and iterate through each of the images where the crop faces, restored faces, and restored images are generated from the GFP-GAN, and then they are basically put back together in different places. So cropped faces is just it's just the aligned cropping of a photo from the input. Restored faces is the same thing, but restored and upscaled, and restored image is the whole image being considered. So crop faces will, only have a certain number, I can't recall the exact number, a certain number of pixels around where it detects the face to be. For each of these, it saves them. So you'll have 3 folders, one for each the crop faces, restored faces, and restored image. And yeah, and then it outputs the restored image essentially. So pretty straightforward. We can actually get it to run here in our notebook now. So I want you all to go to run-gfpgan.ipynb, and then you can just go ahead and hit run all. I've already done this, so mine's going to be a little faster than y'all's. Because I don't actually have to do any of these installs, or this wget for that matter. Ugh. Oh well, I'm getting a second model. There we go. All right, and then if you scroll down after you hit run all, you'll get to where the actual demo is running. And we've got our arguments here, upscale 2. Our test path is our inputs, whole images, which we can see here on the right, which has 3 photos. We're going to save to results. And our model path is, oops, sorry, experiments, pre-trained models. And we are using real ESRNet. Oh, so sorry, run all is in the top right. Right next to the account settings, share, and restart kernel. So sorry. Okay. Oh, sorry, y'all. It seems that I didn't make a results folder. So sorry, one sec. Okay, there is a results folder. Occasionally, you'll run into this on gradient notebooks where the sidebar isn't fully loading. You can just refresh your page, although I recommend you wait until your processes have stopped running. And it should be there. Yeah, there we go. Okay, cool. So let's look at our inputs and then compare them to our now upscaled photos. So here we got a picture of what appear to be sisters or Sergio. It's in the top right under account. Are you? Oh, Sergio, did you go to run-gfpgan.ipynb? If you're still in inference.py, there won't be a run all button. So that might be why. If you go to here, there will be cells to run. So the run all button will be there. But you can also, got it. Awesome. Wonderful. All right. Just want to make sure. you were able to follow along. Got picture of, I'm guessing 2 sisters. I don't mean to assign gender, but looks like 2 sisters. And here is our upscaled version. Kind of hard to see how much higher quality it is in this one because our original input seems like it was already okay quality, but I'd argue that there's some noise that's present here on the face that I'm not seeing in the upscaled version. But maybe this isn't a great example. Let's look at another photo. Oh, I recognize him from the big collage. So we got what appear to be relatives with a younger daughter. I'm guessing this is a christening or something like that. Let's look at the restored and upscaled version. Oh, sometimes things don't want to display properly, so you can just shrink the page like this. So we've got a pretty sharp rising quality. I wouldn't call this as good just off the bat as the version submitted in the paper, but I would say that's a distinctly upscaled version of his face. The woman's face seems to be the best, but there still seems to be some extra lines and artifacting being added in. And this eyebrow is curved oddly, I would say. It looks like there's an impression of an eyebrow right here as an artifact. And most of the girl's face is fine, but we've got a demon eye for whatever reason. So it's not a perfect upscaling, but it does fairly well, especially compared to the competition. And we'll finally close with this picture of Blake Lively. I like this example a lot because you can clearly see the noise all around on her face, and we can contrast it with a less noisy photo side by side. And we got to, I think because of the lack of information due to the noise, we get a smoothing effect on the face. But I'd say the detail is still mostly all there. I would say this is probably the best upscaling of the selections we had. And her face also looks fine, but it was already relatively high quality. But there's no artifacting on the face here, which is really nice. You can also see how there's still all this noise in the background. So maybe real ESR-GAN wasn't super successful here. As you can see, all of these are not perfect, but it is truly on the bleeding edge right now. And compare this to working for 2 hours in Photoshop, and you'll see the convenience of something like this. All right, so 2 more steps. You can directly upload a file using this little cloud up arrow button in the bottom left. So I've got my sample photo here. All right, let's go back to my notebook. And I've uploaded it into my restored. Oh, I put it in restored images. Shoot. Okay, excuse me. If you are clicking on a folder and operating in a folder and you use the upload button, it'll upload into that folder. So keep that in mind. Let's see, in the results. Test.jpg to inputs / whole images. Yeah. Okay, so now I've moved it, and then you can, now that I've uploaded it, I can rerun my inference GFPGAN.py script. And it'll iterate through each of the photos again. While we wait, I'm going to answer some questions. I'll ask, how do we know super resolution is representative of the actual person captured in the photo, i.e. it doesn't change how that person looks like? That's an excellent question. The answer is the algorithm can't tell. You can do it yourself and manually see that with your eye, but oftentimes, I should say, not all the time, it's a failing of the model itself to actually be able to do that. We can look back at that example. Oh, right, that's how this works. Okay, let's just blow this up. So, look at the pulse model here. That's clearly causing that situation to happen. I use refresh your page. Sometimes the IDE doesn't display folders when they're created. It's a frustration. I'm sorry about that, but you should be able to access it if you refresh your page. Going back to Ola's question, yes, sometimes you will see faces that are not correct, and it's really up to the operator to modulate the model as needed to try and counteract that possibility of that happening. Because it looks like Amy Poehler's face is on this little girl here. Okay, now that that's back to run, let's look at our image. Look at that. It is 2 times larger, and those are some nice clear faces with minimal artifacting. I mean, got this cheek thing going on here. That's about it. All right, cool. So that's how you run a notebook using GFP-GAN. We've got 3 minutes left, and I'm going to close with actually deploying GFP-GAN as a Flask app. I'm going to go ahead and say right now, I am not a front-end developer. So this is the extent of my front end. Please don't judge. All right. So if everybody could do me a favor and go back to their console, and within the team they were just working in, or project they were just working in, or any project you really, go ahead and click on Deployments tab. Can I get a B's that we are all there? Beauty. All right. So go ahead and click create, just like when we made the notebook. Oh, actually, sorry. There's actually instructions for how to do this on the second to last slide if you still have your slides. So yeah, you go to the console, select your team project, click create deployment. Then under run your first deployment, which is right here, find the link that says upload a deployment spec and click on it. This will allow you to directly input your deployment spec. And then within the slides, I've actually shared everything to make the deployment. So just copy this, head back over, replace it, and call it whatever you want. I have this running on a P4000. Oh yeah. Here is the YAML spec. You might have to do the indentations manually. I'm not sure if that will transfer over from the chat, but so make sure to indent by at least 2 spaces, replicas, and instance type. I'm using a P4000 for this deployment. Gradient has a lot of different, like a pretty wide variety of GPUs. P4000 is one of the weaker ones. You can feel free to use whatever one you think is ideal for your use case. But it's worth mentioning that we currently don't allow deployments on the free GPUs. So you will need to upgrade to a paid account if this is something you're interested in trying out. But I've already made the deployment myself, so I can just share the link with all of you, and you can try it out yourself. Otherwise, you can make your own deployment, whatever you prefer. But if you go to the link I just shared, you'll be greeted with this screen, upload new file, and that should say upload. Oh, well. And you'll have an option to upload whatever picture. So let's just use my test photo that I got, test.jpg, tried and true. And then when you hit upload, it'll upload the image and run the model to upscale and restore the picture. It doesn't have a cache, so it can only do 1 image at a time, but it's lightning fast. As you can see, I'm already ready. So this is your opportunity. Oh, I'm so sorry, y'all. I was sharing with hosts and panelists. Thank you for pointing that out. I don't know when that switched. Okay, here is the deployment spec. And here is the link to the Flask API. And I encourage all of you to mess around with this. There's a lot of applications for being able to quickly and effectively upscale and restore pictures. I had a lot of fun with my family just doing it with my dad's grandparents' pictures and things from back in the day. And I encourage you all to play around with this, and who knows, maybe you can make the next cool web app with Gradient. But that's the end of our session. I do want to point out that there is a resource list in the very last slide. I'm going to go ahead and share that right now in the chat. The things that are probably most worth checking out are my 2 blog posts, which cover essentially the same material we talked about today. So if you ever need a refresher or want to understand more thoroughly what's going on, that's a good starting place. The original GFP-GAN GitHub and our fork, and the original papers for GFP-GAN and real ESR-GAN. They're dry reads, but for machine learning papers, I actually found them really interesting. So give it a whirl if that's something you are interested in. But otherwise, I'm going to open the floor for questions now. I did see Ariel's question, and I actually don't. He asked, what is the difference between transformers and attention networks? I haven't actually worked with attention networks, so I'm not sure if I can give you an effective answer. Let's see. A cheeky Google. If there are no more questions, you are all welcome to leave. Ayush, good question. They are not really being stored. So I am actually, every time you run the upload button, it is actually deleting all of your the previous images that you had stored. I just wanted this to be as lightweight and quick as possible, so there's no cache, there's no storage. It just does the one photo, outputs it, and then it's in the ether. An enterprising individual could definitely flesh that out a little bit more. But if you go to the GFP-GAN repo, let's see. You can see the myapp.py that this is based on. And there's a few things I could point out, actually. This doesn't seem to be updated. Huh. Maybe it's apped up. Excuse me, I must have actually, sorry, I included an artifact in the GitHub. I'll remove that later. But the app.py in GFP-GAN is where I made my deployment. So it's using the inputs whole images from the repo, because I'm pulling in the repo in the Docker container this is built off of. But when it gets uploaded, let's see, where is it? Oh, maybe it is in main, actually. So I haven't looked at this in a month, so I'm not sure where I'm deleting it, but that is what's happening. It's deleting the photo, but it's originally being stored in the whole images folder, much like we had in here, because they're built off the same container. Or sorry, GitHub repo, not container. It's all on a, oh, well, I suppose I did make a container, but the container I made has the GitHub repo. If you're also interested in what the container entails, you can see that here in the Docker file. All right. Are there any other questions? Ariel, I'm sorry I'm not confident answering yours because I haven't worked with attention networks. Oh yeah, thank you. All right. Yeah, thanks so much. I still really appreciate the good question. Like I'm gonna go research that now. It's always fun to be told about something you don't know when you're teaching. Yeah, thank you so much, Ala. Thanks, David. Thanks, Ariel. Thanks, Mika. Misha? Misha? I'm so sorry if I'm mispronouncing that. Thank you, Sergio. Thank you so much, Ayush. This was a great session, y'all. Yeah, absolutely. We'll be having our next one. Oh, that's important. Next one will be in a month. So look out for that email. We're going to aim for a more regular cadence. So this should be around the same time next month, around the 26th. All right. Bye-bye. Thank you so much. Thank you, Ala. Thank you, Martin. Thank you, Barry. Thank you, Agata. Or Agata, please excuse my pronunciation again. Thank you, Harish. Not topic for next month is being deliberated on. I'm really vacillating between StyleGAN 3 and talking about the new signal uptake processes that are inherent in the new iteration of StyleGAN, and doing a not gradient talk, but actually core, and talk about making a hybridized recommendation system using Spark. I'll be deciding in the next couple days which one that would be. Yeah, it's really cool. Yeah, so glad you all could come. If there aren't any more questions, I will now just end the call, but let's see. Let's just run through the names. Thank you, Agata. Thank you, Allison. Thank you, Ariel. Thank you, Barry. Thank you, Debabrata. Thank you, Guntis. Thank you, Harish. Thank you, Kalyan. Thank you, Lenny. Thank you, Martin. Thank you, Micha. Thank you, Nana. Thank you, Nombre. Nombre apellido. That's amazing. Thank you, Peter. Thank you, Raghuvansh. Thank you, Sergio. Thanks, Steve. This was a wonderful session. Y'all were wonderful attendees. Really looking forward to seeing you all at the next one. Make sure to check out the Paperspace blog for updates from me, and have a wonderful rest of your day. Bye, bye, bye.